Okay, so in the last lesson we looked at sequences, and we sometimes had some pattern where we noticed that the numbers in the sequence were going up by the square numbers. So 1, 4, 9, 16, 25. We said the nth term for this was n squared. And then we had another problem where instead of starting at 1, it started at 3. But then it was 3, 6, 11, 18, 27. So we noticed that it was exactly the same as n squared, but each time we were adding 2 on top. So the nth term was n squared plus 2. And when we had other examples of the same kind. Now we're going to look at more into that, and these are called quadratic sequences. So quadratic sequences use the square of the n instead of just the n itself. Now they can be in different forms. The simplest form is t equals n squared plus a number, or t equals 2n squared plus a number, or 3n squared, etc. So we're going to have a coefficient in front of the n squared. That is the simplest form. Now there's another form. So the simplest form we can say, instead of coefficient we can call it a, and for the number we can call it b. So the coefficient we're going to call a, and the number we're going to call b. And that gives us a simple form of t equals a n squared plus b. Now there's another form which we will look at more next lesson, where we can have something a little bit more complicated, also involving the n squared, but where we also have some sort of n in it as well. So we might have a equals 3n squared plus 2n plus 5, where we have a number in front of n squared, another number in front of n, and then a number. And that would be the most advanced version of a quadratic sequence, with not only n squared but also with n. But the same sort of general principle will still apply. Okay, so we now have a simple form that we looked at, and also a general form that we looked at. Now when we did the work on the simple quadratic equations like these ones, we noticed that we were trying to see, is it going up by a single number, is it linear, and we kept finding it's not. But we might have noticed, and here we noticed that we're going up by the same amount as the one above. Now you might have noticed something peculiar happening, which is that even though they go up by a different number, once we know that this one's gone up from 3 to 5, we can sort of notice that this one has gone by another 2, and then another 2. So this is what we're going to be interested in, that here actually, from here to there is plus 2 plus 2. From here to there is plus 2 plus 2. So we're going to be interested in what's happening with the other types of sequences that are a bit more complicated. So let's take, for example, 2n squared plus 1. Now what would be the first term of that? Well, if n is 1, then 2 plus 1 is 3. Now the second term is going to be 4 times 2, 8, plus 1, 9. The next one is going to be 19. Then we're going to have 33, and then 51. Now, if we're trying to make them see if they're linear, we would find they're not linear. So here we're getting plus 6, plus 10, here we're finding plus 16, and here we're finding plus, I made a mistake, yes, plus 14, and here we're finding plus 18. Now again, what we're noticing is if I'm looking from the 6 to the 10, I'm finding I'm going up by 4, and here by 4 again, and here by 4 again. So the same pattern seems to be happening. When I look at the difference of the difference, then I get always the same number, and that is called the second difference. It's the difference of the difference. Now what if I had this complicated one, 3n squared plus 2n plus 5? What would be the first number? Well, first number n would be 1, so 1 squared is 1 times 3, 3 plus 2 times 1, 2 plus 5, total 10. Then the second would be 21, 38, 61, and 90. So again, each time I'm replacing the position for n, and I can calculate the term. Now if I look how I go from 10 to 21, I've added 11. From here to there I've added 17. From here to there I've added 23. And from here to there I've added 29. Now if I went one more, I suspect I would add what? Well, what is the pattern we're noticing on the second difference? We are adding 6 each time to the second difference. So if we added 6 here, we would be adding 35, which means we would be at 125. And we can check that. That should be this term 1, 2, 3, 4, 5, 6, and use 6 here, and we will find that number. Right, so what we're noticing is it works for every single quadratic sequence, that the second difference is always a fixed constant. Now, how does it work with the actual nth term? Well, the other thing we might be noticing is when I had a simple one, which was just n squared, or n squared plus 2, the second difference was 2. So when I have nothing here, or nothing being 1, 1 becomes 2. Here, when I have a 2 in front of the n squared, I get a 4 as a second difference. And when I've got a 3 in front of the n squared, I get a 6 as a second difference. And generally, we can prove that more mathematically, but you don't need to at this stage. We will find that to find the second difference, it is 2 times the coefficient in front of n squared. And that is very important finding, which we will use when we want to do the opposite process of looking at the numbers, finding the second difference, and then we know we just have to divide by 2 to find what comes in front of the n squared. Okay, so we have figured that the second difference in a quadratic sequence is always this as a fixed number. But now we need to work out from a sequence of numbers, we want to actually find the nth term when it turns out to be a quadratic sequence. So let's take an example. For example, we start with -1, 2, 7, 14, and 23. Now at the moment I'm not sure what's happening, so I always have a little look at whether they're going up as a linear, and they're clearly not. But as I'm doing that, I'm also noticing the pattern that I seem to be adding 2 each time. So here, when that happens, then I know for sure that I've got a quadratic sequence. So it's the second difference is constant, I know I've got a quadratic sequence. So my quadratic sequence is going to look something like t equals an squared plus bn plus c. But I don't really know anything about any of these a, b, and c yet. Or do I? Well, I do actually know something about the a. Because if it goes up in 2's, then we know that the a is going to be half of that. So a equals 1. So we know that the sequence is going to start looking like n squared plus something, which may have some n and may have some numbers, or may just have numbers. So how do we find that out? Well, we first work out what n squared would be just on its own. I need to move this a bit. Just on its own, it would be 1, 4, 9, 16, and 25. So now what I do is I do the difference with the original sequence. So my original, my n squared is not the same as my sequence. So if I start with my sequence and I compare with n squared, my sequence is 2 less than the n squared, and it seems to happen all the time. Oops. Minus 2, minus 2, minus 2. So if I start with n squared, I would have to take away 2 to get to my sequence. And I seem that the only thing I need to do. So in the end, my sequence is n squared minus 2. Well, we're going to do a second one before you have a go yourself. So what if we start with 5, 11, 21, 35, and 53? But again, we check the first difference. We get 6, 10, 14, and 18. But when we looked at the second difference, we notice we get 4 each time. So we know we're going to have a quadratic. And we know it's going to start with 2 n squared plus something. Because from the 4, we divide by 2 to get the coefficient in front of n squared. Now we don't know what's the question mark, so what we do is we take away 2n squared from the current sequence to see what's left. And then we deal with what's left. Now what we know from the general form, which we had here, is the what's left is either going to be just the number, or it might be a linear sequence. But we know how to deal with linear sequences. So either way, we will find what's left. So first we need to work out 2n squared. So 2n squared, we would have n squared being 1 times 2, 2, then n squared being 4 times 2, 8, then we have 9 times 2, 18, then we have 16 times 2, 32, and then 25 times 2, 50. In this case, now we're going to see the difference between the sequence minus 2n squared, and we find that 5 minus 2, we've got 3 left, 3, 3, 3, 3. So in this case, the what's left, what's on top of the 2n squared is 3. So t equals 2n squared plus 3. Now, as I said, today we're doing all these more simple ones with just a number after the square element, and next time we will do more complicated ones with n's as well.